Hi, I'm Reverend Greg, and I welcome you to this video in the tutorial series Shaders for Hobby Programmers. This time we will create our first very simple shaders. Simple because there's only little code used and they don't need texture codes or additional textures. We're going to create 3 shaders today: a simple alpha shader, an invert color shader, and a desaturate shader. The first 2, in my opinion, are of no practical use in a game, but will be great to just show a few things and to getting used to shaders. The desaturation shader, I guess, can be really useful already though. Here's a quick peek at the code and result. If you already know from the start what this code does, then this video will be too simple for you, and you probably want to skip it. A short disclaimer. This tutorial series is mainly for hobby programmers who struggle with understanding shaders. I'm not a professional programmer and I'm not very good at maths. The goal of this series is to pass things I learned about shaders on to other hobby programmers. So if you see any mistakes in my video or see a better way to solve a problem, please add a comment for everyone to learn from you. But let's just dive in and create the first simple alpha shader now. So I'm just going to create a new shader and name it Shader Simple Alpha. And then I'm going to create a new object. Well, if you want to, you can use the base project I'm using. There's a link in the description where you can download it. I'm not actually creating a new object, I'm just copying a template I created earlier. And I'm renaming it to Object Simple Alpha. When looking at the draw event, you will already see 2 important lines for using of shaders. One is shader set and the other one is shader reset. When working with shaders, you need to tell GameMaker Studio what shader to use for the coming draw functions you're using. And that's done with the function shader set and then the ID of the shader. I'm going to create the ID in the create event and just store it in the variable shader. And once you're done using that shader, you need GameMaker Studio to turn that shader off again. That doesn't mean GameMaker Studio is not using a shader at all. It's just switching back to its standard pass-through shader. Now in the create event, I'm just going to add some info for my standard object, so when I run the project, it will show what shader we're running on. It will just show that info text on the screen. Now this shader is actually just, it will just change the alpha of the sprite, and thus it's pretty much useless, because you could as well just use the functions draw sprite x or draw surface x. And of course we will need a sprite to draw. I'm just picking one that is in the base project already. You can use any sprite actually. And here I'm also storing the shader ID in the variable shader so I can use it later. Now let's run the project and see what happens. Okay, seems I forgot to add the object to the room, so let's do that and run the project again. What I expect to happen is that the sprite is drawn as if I hadn't set any shader at all, because we didn't change the shader yet, and so it's just a pass-through shader at this moment. But yes, that's working. It's just showing the sprite as it is. Now let's change the shader code. First thing I'm going to do is splitting up that one line in the main function to 2 lines. I want to create a variable called base color and store the interpolated vertex color and the pixel color in the new variable base color. Now VV color is a vec4 and texture2D returns a vec4 as well. VV color is the vertex color and texture2D returns the pixel color at a specific position. The pixel is fetched from the GM base texture at the position VV text chord, as we learned in the introduction video. GM base texture is a sampler to the data type and just actually holds the sprite on the surface we're drawing. Texture 2D also returns a data type of vector4, so VV color times texture 2D will be of the data type vector4, and thus we need to declare base color as a vector4 as well. And GLFrag color is a vector4 as well. It's the output of the fragment shader. It's just the color that is going to be drawn. And I could just set it equal to base color and still have a pass-through shader. But we want to change the alpha. So I'm taking the base color.rgb and the base color.a times a factor times 0.5 and construct the vector3 base color.rgb and the base color.a times 0.5. I construct those as a vector4 and set GLFrag color to the result. So what we should get is just normal color but with half alpha. So let's run this and see what happens. And yes, it works. But now let's add a uniform. Let's call it uniform alpha. As mentioned in the introduction video, uniforms are variables we can use to pass data from GMS into a shader. So let me show how that is done on the GMS side. First, we need some kind of handler. This is not GMS specific, that's from what I can tell from other tutorials, that's something you need to do in any programming language. You just create a variable and use the function shader getUniform, shader ID, and the name of the uniform as you named it within the shader, in our case alpha. Naming this handler uAlpha, so I know it's handling the uniform, and whenever we set a uniform we can refer to this handler, the uAlpha, to tell GMS which uniform within the shader should be set. And that's what we are going to do now inside the draw event. The function to set uniform is just called shader set uniform, and then, for example, in our case, f for float. Then we need to pass in the handler. That's the handler we just created in the create event, uAlpha. So shader set uniform f knows which uniform to set. And then we set the value. I'm using something I prepared in the base project. There's a slider in each room that can set a value from 0 to 1. And it's called globar.slider1. Actually, there's two sliders, slider 2 and slider 3 as well. If you're not using the base project, you can just create some kind of timer, for example, or some other ways to pass in a value ranging from 0 to 1. I'm just using the global.slider1 because that's one of the reasons I'm using this base project, because it's so simple for me to test things. So let's run this again and see what happens. And of course, once again, I forgot something. I actually just forgot to use the uniform to calculate the alpha. And there's still 0.5 there and should be alpha. Let's run again. And yeah, it's working. We just created our first shader. So let's close this and let's go on to the next shader. Now we will create a color inversion shader. First, I'm quickly going to create a new shader called shader invert color. Again, we won't need the vertex shader. I'll just once again duplicate my standard object. I decided to not use a uniform with this shader, so I'll just delete that line in the draw event. And in create event, I set up some basic some basics for my standard object to work properly. The info text, the sprite, and the shader we just created. Here as well, I'll just remove the uniform line for this shader and place the object in my test room. If you're using my base project, always make sure to place the modules in the main layer, not on the top layer. When creating a shader, like when creating any program, you need to first think about what exactly you want to do. So in our case, we need to think about what inverting color actually means and how that could be coded in GLSL or pseudocode. And I'd like you to pause the video and really think about what color inversion actually means and what it is. So, thought about it? So here's what I think color inversion is and how I plan to code it. If I invert a grayscale, that would mean swapping dark with light. So black becomes white and white becomes black. Dark gray becomes very light gray, and gray slightly above average luminance will become a gray with slightly below average luminance. So I think color inversion is doing the same thing to red, green and blue, but not to alpha. So if red is 0.2 beneath a maximum of 1, then the red channel's output should be 0.2 above the minimum of 0. So a red value of 0.8 becomes 0.2, and the same for the green and blue channels. To express that in code would then be something like red new equals 1 minus red old. So let's do that in our fragment shader. The first thing I do, like always, is split up the GLFrag color line into 2 lines. Just a quick repetition here. In one line I create a vec4 base color. On the right side of that equal sign there is VV color, which is of the data type vec4 as well. VV color is the interpolated vertex color between the vertices. That interpolated vertex color is multiplied with the pixel color of the sprite or surface we draw at an interpolated texture chord. GM-based texture is of the data type sampler 2D and holds the texture we're drawing. VV text chord is the interpolated coordinate of the vertices on the texture, and the function texture2D returns the pixel color of that texture on that interpolated coordinate as a vec4, and so the right side of the equal sign is a vec4 as well. The second line for now sets the output of the fragment shader, the vec4 GLFrag color, to the vec4 base color we just created. So like this is still just a pass-through shader. Now let's add the inversion code in between. I'll just write the pseudocode from earlier as a GLSL code now. Basecall.rgb, a vector 3, is set to 1 minus basecall.rgb. As I've shown in the introduction video, subtracting a vector from a float means each component of the vector is subtracted from the float and the result is still vec3. The red component will be 1 minus red, the green will be 1 minus green, and the blue will be 1 minus blue. So we don't need a vec3 constructor for this to work. Now let's run the code and see what happens. It works. The colors are now inverted. And to once again show what VV color does, the vertex color, let's change the draw sprite code to a draw sprite ext. Sprite, subimage, x, y, x scale, y scale, rotation, red as color, and alpha 1. And see what happens. Some viewers might be surprised by the outcome. We told GMS to draw red, but the output is cyan and has a very high luminance. Let's have a quick look at a RGB color wheel. Here you can see that cyan is opposite of red, so cyan is the inversion of red. With cRed in the drawSpriteX function, we have set the vertex colors of our sprite to red, and our shader inverted the vertex color to cyan. And since our shader multiplied the vertex color into the pixel color, and the vertex color red has a luminance of less than 1, the base color was darkened, but when inverting, the luminance got inverted as well. The result is that light cyan color. If we turn off the shader and run the program again, we'll see the sprite overlaid with red and much darker. Now if we go back to our fragment shader and move the interpolated vertex color from before the inversion to after the inversion, you can by now probably already predict what happens. The sprite is drawn red because the vertex color now overlays the inverted pixel color, but the luminance stays inverted. What was originally dark, like the plant in the foreground, is now a light red, and what originally was light, like the white wall, is now dark or even black. Anyways, second shader done, so let's move on to the last shader for today, and this one I think can actually be used in games. A desaturation shader. Again, I'll start by creating a new shader, duplicating my standard test object, placing the object on the main layer of my test room, and setting up the standards, info text, sprite, and shader. This time I'll use a uniform again for the desaturation strength, and I'll set it up right away. In the create event, I create a handler uStrength, which will tell the shader which uniform to set, and I need to tell which shader this uniform can be found in and what the name of the uniform within the shader is. So I'm calling this uniform strength. In draw event, after setting the shader and before drawing, I'll set the uniform by passing the handler and a value. I'm using the linear tween of my basic object again, global.slider1, which returns a value from 0 to 1. But if you're not using the base project, you can set any value from 0 to 1 or create your own tween. Quick check if everything works so far. And it does. So before we write the shader, I again would like you to pause the video for a minute and think about what desaturation really means and how you would write a pseudo or GLSL code. Got a solution? So here's what I think desaturation means. If we desaturate completely, everything is gray. And a color is gray if red, green and blue all have the same value. To still keep the contrast, each pixel needs to stay as bright as it was before the conversion. A simple way to achieve both would be value equals red plus green plus blue divided by 3. A partial desaturation would be achieved by moving each color channel towards the gray value of the color, so we'll need a desaturation strength factor that sets how much the channels are pushed to that average gray value. The code would then be something like this. Red new is red old times 1 minus strength plus value times strength. Green new equals green old times 1 minus strength plus value times strength, and blue new would equal to blue old times 1 minus strength plus value times strength. So it's time to code this. I'll start by transforming that pseudocode to GLSL, and then step by step for tutorial purposes change the code to a more efficient and readable state. Let's start by splitting the glfrag caller line again as we did before. Version 1 is going to be overly long and is just a one-to-one conversion of that pseudocode. First I create a new float called value and add up the red, green and blue value and average them by dividing by 3. Now I create a vec3, the out color, and for each component I insert the formula I wrote in pseudocode. So that's base col.r times 1 minus strength plus value times strength. And the same for green and for blue. The output color will now be the same as the base color when strength is 0, will only be the average value if strength is 1, and be anything in between depending on the uniform strength. Let's set glfrag color to the output color, but don't forget glfrag color is a vec4 and the out color is a vec3. The alpha component is missing, but we can get that from the base color. To create a vec4 from out color and base color.a, we need to construct a vec4 like so. Vec4, out color, base color.a. Now let's run the program. As you can see, this works, but there has to be a more elegant solution, so let's do version 2. Here we make use of the knowledge about how floats and vectors can be mixed. If we add, subtract, multiply or divide a float and a vector, in our example a vector 3, the result will be of the same data type, a vector 3. This means we can simplify the code. Float value stays the same, but vec3 out color now simply is base col.rgb times 1 minus strength plus value times strength. Value and strength are floats, so value times strength is a float still. And 1 minus strength is a float as well. The vec3 base color RGB times a float will still result in a vec3. Each component, red, green and blue, are multiplied by 1 minus strength. Then the float value times strength is added to each component of the new vec3, and the result is a vec3 again. Let's comment out version 1 and run the program again. And it still works, but there still has to be a better way. On to version 3. Introduce the mix function. First, let's just grab the float value from before. This part remains unchanged. Now let's create a vec3 out call again, but this time by using the mix function. Mix takes 3 arguments: a first value, a second value, and a mix amount. If the mix amount is 0, the result of the mix function is value 1. If the mix amount is 1, the result of the mix function is value 2. If the mix amount is 0.2, the result of the mix function is value 1 times 0.8 plus value 2 times 0.2. So it's the same as lerp in GMS, and it's pretty much what we did in version 1 and 2, but this time in a neat little mix function. The values can be floats or vectors, but both values have to be of the same data type. We want to mix the original vec3 color as value 1 and the average value as value 2, but the average value we created is a float, and we cannot mix a float with a vec3, so we need to construct a vec3 from a float. As shown in the introduction video, we could construct that with the code vec3 value value value. But since all three components are the same, we can use the short version and simply write vec3 value, which constructs a vec3 with all components set to value. So our line looks like this: mix basecall.rtb vec3 value strength. Let's comment out version 2 and run the program again. And it still works. Now in version 4, I'm changing the way we calculated the value. Here's the thing: the luminance of red is not perceived the same as the luminance of green or blue. But in the code we used so far, we didn't make a difference. Now, I don't consider this a big problem because it's not really that far off, and if I wouldn't compare the results side by side, I wouldn't be able to tell a difference. But let's do the quote-unquote correct way anyways. Correct is still relative, by the way, so there's even different conversion weights used, and I never really understood why. So in our example, I picked the NTSC conversion. This means that 29.9% of the red value should contribute to the luminance, 58.7% of the green value, and only 11.4% of the blue value should contribute. Whereas in our previous version, each channel contributed 33%. The line would change to this then: float value equals basecall.r times 0.299 plus basecall.g times 0.587 plus basecall.b times 0.114. And now let's run the program again. And of course it still works, but I'm not going to show you the difference to the 33% contribution for each channel. If you want to compare, duplicate the shader and the object, tweak one and run both at the same time, or just make a screenshot of one version and compare. You definitely will notice a difference, but in my opinion, not in the sense of one looks always better than the other. The NTSC is just closer to reality. You could, by the way, take completely different weights and compare those. Nothing stops you from dropping green to 0. And if you don't want to, you don't even absolutely need to lift the other values as compensation. The image will just darken more if you don't. In the end, I don't think it matters which looks more realistic. In the end, it just matters which looks best. But now the last version, introducing the dot product. The dot product is a vector multiplication, but not component-wise, as for example in VV color times texture 2D. The dot product works like this. Multiply the first component of both vectors, then add the multiplication of the second components of both vectors, and then add the multiplication of the third components of both vectors. So, A1 times B1 is a float. A2 times B2 is a float as well. And so is A3 times B3. Adding all those up still results in a float. So the result of a dot product always is a float and not a vector anymore. This of course also means both vectors need to have the same size. You can't just create a dot product with a vec3 and a vec4. Let's have a look at the code with the dot product now. Float value equals dot basecolor.rgb and the vec3 constructed with 0.299, 0.587, 0.114. So that would be red times 0.299 plus green times 0.587 plus blue times 0.114. And that's exactly what we did before, but this time using the dot product. And if we run the program again, this of course still works. Now again I want to show you what vertex color is and what the interpolated vertex color VV color does. In GMS, let's replace the drawSprite function again, but this time with the drawSprite general function, because this one lets us set the color for each of the 4 vertices of a sprite individually. drawSprite general, sprite subimage. I'll just create 2 vars with sprite width and height to make the code more readable. And left, top, width, height, X, Y, X scale, Y scale, rotation, C red, C green, C yellow, and C blue, and alpha 1. And run the program. Since VV color is multiplied in before the desaturation, it will be desaturated as well. As you can see, we set the upper left vertex to red, the upper right to green, the lower right to yellow, and the lower left to blue. In between, we see all kinds of interpolated colors, and that's what VV color is. Each time the fragment shader calculates the color of a pixel, the GLFrag color receives an interpolated color value and not the vertex color. If again we move VV color to the end, the desaturated color gets overlaid with the interpolated vertex color. But in this shader I really prefer to have the vertex color desaturated as well, so I'll move it back up. And if you don't want the vertex color at all, you can remove VV color from the fragment and vertex shader, and even in color from the vertex shader as well. Now all that's left for me to do is to clean up my base project a bit. I'll create 2 new room children, name them room simple shaders and room desaturation, and move the objects we created today from room test over to the new rooms to have some testing space again. I hope you learned some interesting stuff about shaders in this tutorial and are eager to learn more. In the next video, I think we'll have a look at gamma, brightness, contrast, and saturation. Until next time.